Lunch and Learn. My name is Franco Rotoli. Today we're going to be talking about adaptive meshing in SOLIDWORKS simulation and making sure your SOLIDWORKS simulation results are correct. Utilizing adaptive meshing techniques is one of the most important ways you can have confidence in your simulation results. During this session, hopefully we'll understand the importance of having an accurate mesh. Let's take a look at today's agenda. SOLIDWORKS simulation has a couple of different types of mesh with a few different meshers. We'll discuss these first. Once we understand all of our different meshing options, we can delve further into adaptive meshing. We'll then discuss a few different methods to post-process our simulation results and verify that we have come to convergence. Just as a reminder, before we get started, mesh refinement is not the only variable in coming up with a correct solution. Making sure you have the right inputs, restraints, and contacts is just as important. It's always a good idea to verify your results with empirical testing and hand calculations if you can. All right, let's get started. SOLIDWORKS simulation offers three types of elements: solid, shell, and beam elements. We use solid elements for most circumstances. They're the most robust and versatile. Shell elements are used for components with consistent thickness. Think sheet metal, plate steel, or even composites like carbon fiber or circuit boards. Beam elements are used for structural members with a constant profile along the length. These are for structures like machine frames or beams or truss structures. Currently, adaptive meshing is for solid elements only. So the rest of the session, we're going to be focused only on solid elements. Okay, so in the realm of solid elements, we have two options: draft quality and high quality. These are also known as first and second order elements. A draft quality element has four nodes and linear sides, or legs. The nodes are where the solver actually runs its equation, so it's important that these nodes and consequently the elements match up to actual geometry as close as possible. As you can see here, with draft quality mesh, the elements don't do a great job of matching the real geometry. The holes and nonlinear edges end up being oversimplified and really faceted. I could go ahead and shrink the mesh down quite a bit and get a better resolution in the areas where it's faceted, but as you can see in the next slide, that's not going to be necessary. A high quality element has the same four nodes as draft quality, but also has mid-side nodes, bringing the node count to 10 for each element. Notice the legs of the tetrahedron are now flexible and can match up more closely to our geometry. Here's a side-by-side comparison of the two meshes. So you might ask, why would I ever use draft quality elements? Well, the answer is simple. The same reason you write draft copies of term papers. You want to get a rough idea if your part is going to react properly based on your other inputs. I don't know about you, but I'd rather have my solve time be a couple of minutes than waiting 3 or 4 times longer just to still get the wrong result. When we jump over to the software, I'll show you where that option is in the mesh creation dialog. So what I typically do is my first run or two possibly are with draft quality elements. I don't really worry about mesh refinement all that much. I just want to make sure all my inputs are good, and then I move to high quality elements. So speaking of mesh creation, let's take a look at our options. SOLIDWORKS simulation offers 3 different meshing algorithms to determine a mesh for our models: standard, curvature-based, and as of SOLIDWORKS 2016, blended curvature-based mesh. The standard mesher allows you to specify a global element size with a plus or minus tolerance. It will attempt to make every element in the model fit these criteria. There's some other error checking options in here, but that's a topic for a whole nother session, like automatic transition and some others. But again, we can discuss those in a different session. The curvature-based mesher gives you a little bit more control over the element sizes. It allows you to define an upper and lower limit to the elements. It also allows you to define how many elements fit around a circle or hole, and also a growth ratio, which will tell it how fast to transition between small and larger elements. This mesher will automatically add small elements to small features like fillets and small holes, and it'll use the larger elements in large open areas of the model. Finally, the blended mesher has the same inputs as the curvature-based mesher. It just uses a different algorithm to map the elements through the thickness of the part. Use the blended curvature-based mesh for models that fail to mesh with a standard or curvature-based mesh. It also has this button right here. This button will find the minimum radius of curvature in your model and suggest that you use that as your minimum element size. So now that we have meshed our model, we move on to the question that's most likely brought you to this webinar. What is adaptive meshing? What exactly is adaptive meshing? Well, it's fairly straightforward. Adaptive meshing, whether done manually or automatically, is simply coming up with what we call a mesh-independent solution. All right, so what does that mean? Let's take a look at this simple example. If you've taken our simulation class, you likely recognize this model. It's fixed on the back face and a load is applied to a split line ring around the central hole. Symmetry is also added, but we're not going to worry about that right now. I meshed it with whatever default mesh simulation deemed was okay. We see that we get a max stress sort of where I would expect it with a value of about 183, 184 megapascals. Okay, great, I'm done. I can go to lunch, right? Well, let's hang on a second. The elements around the fillet look a little large. Let's add some mesh control and see what happens. Same global mesh, but now the fillet has a 3mm mesh control on it. We don't have time today to discuss how to add mesh controls, but if you want us to show you how, feel free to give us a call. Anyway, we see the stress went up by about 10%. Now we're at about 200 MPa in roughly the same location. Let's keep going and see what happens. I have the mesh control again to 1.5mm and we see the stress went up again, this time by about 5%. So we're getting closer to the actual stress value. Let's refine it one more time with a mesh control of 0.75mm and we can see the stress at that location stayed pretty much the same, about 207 MPa in the same location. If we plot these results, we see a very distinctive curve. This is called convergence. We'd probably want more than 2 convergence data points in the real world, but you get the idea. So what I just showed you was the manual mesh refinement and control. Basically manual adaptive meshing. I ran through a rough mesh, refined it manually in the areas of my concern, or what I thought were the high stress areas. This method is fine for simple studies, but as stress profiles and distributions get more complex or in larger assemblies, this can be fairly daunting. Enter adaptive meshing. This screen is located in the study properties of a linear static study. It's set to none by default, which relies on you, the user, to run mesh refinements manually, similarly to what I just did. We also have H-adaptive and P-adaptive options. These options will change our mesh automatically based on the criteria we set up. We'll look at these options as well as our criteria individually. First, let's take a look at H-adaptive. H-adaptive refinement changes the mesh size and density based on where it thinks the high stresses are. It uses the energy norm error to calculate that. We'll talk more about that later. Because of this, your loads and restraints play a huge role as to where the mesh gets refined. Let's take a look at these two examples. The part on the left has a normal force on the front face of the cylindrical body. Notice where the mesh gets concentrated. The part on the right has a shear force of the same magnitude applied. The difference in this case is subtle, but you can see it added mesh in different places. Let's dive deeper into the settings and see what they are. First, we have the target accuracy slider. This is what measures the energy norm error on every element and how it determines where to focus the mesh. It defaults to 98% or 2% error. This is fairly high and can be difficult to achieve, but not impossible. I recommend you keeping this above 95% if possible. Next, we have the accuracy bias slider. This is set to the middle by default. If you have a stress concentrator or singularities in your model, you'll likely want to move this towards the global side as it'll focus on the total energy norm error and not the areas of exponential stress increases. If you're sure there are no stress concentrators or singularities in your model and want to focus on the areas of high stress, you can move this slider to the left. Finally, we have the max number of loops and mesh coarsening. Max number of loops is 5, since we don't want to get caught in an infinite loop if it doesn't converge. You can set this from anywhere from 2 to 5. If we end up needing more than 5 runs to get to convergence, you can just click run again and it'll pick up where it left off mesh-wise and then run another 5 loops. We'll see this in the convergence charts I show in a minute. The mesh coarsening checkbox is a huge resource saver. It'll take the areas of low norm error or low stress and increase the mesh size. So it'll make your mesh bigger to save on computer resources. As you'll see from the following images, Adaptive can create some pretty fine mesh that can take up a bunch of your system resources, so freeing up RAM and processor is a very, very good thing. Okay, so what is Adaptive anyway? And what does it have to do with mesh size? In a solid mesh, the H value is nothing more than the diameter of a sphere that touches all 4 vertices of a tetrahedral element. That's it. There's not any magic, it's just the diameter. So Adaptive is just a fancy way of saying change the element size where needed. So great, with this setting, I can just use adaptive mesh and not have to worry about mesh controls, right? No, not at all. Your starting mesh is extremely important even in an adaptive study. You, as the user and the person running the simulation, knows better than a computer where you want to focus the mesh. You should still add mesh controls as a starting point for the solver. Let's take a look at an example of this. Here I have 2 identical studies. In the one on the left, I started with the default mesh. It came to convergence between 5 and 7 runs with a max stress of about 555 megapascals. That's the 98% convergence that I had requested in the properties. And you can see it converging right in this area. Cool, so what's the problem? Well, let's take a look at the right-hand study. I started with a 3mm mesh, almost 5 times smaller, and ended up converging in about 3 runs with a max stress of about 553 MPa. You can see that right here. With, again, a 1.8% error, right? That's under the 2% that we had specified. With the one on the left, I had to run it twice, and it took about 10 minutes of total solve time. The one on the right came to convergence in the first run in less than 5 minutes. I saved 50% of solve time just by starting with a more appropriate mesh. So again, start with a better mesh and you will typically get results faster. Even though you'd think you're top loading or front loading your analysis, it ends up working out better if you start with a more appropriate mesh. So how do you know if you've converged? Adaptive studies give you a nice little message box once they meet your convergence criteria. If you don't see this box and it just loads the results, then it did not meet the criteria established in the settings. As I mentioned before, just click Run again and it'll start up again where it left off. Just make sure you don't click Mesh again. So don't right-click the mesh and create a new mesh, otherwise it'll start from the beginning and you'll be exactly where you left off currently. So just click Run from the toolbar again and it'll pick up where it left off. Now let's take a look at how to get those convergence charts I showed you before. Once your adaptive study has completed, whether it's converged or not, you can right-click on the results folder in your simulation tree and select Define Adaptive Convergence Graph. This will bring up the property manager, allowing you to plot everything from the actual accuracy it was calculating per run to the number of nodes. Remember, high-quality elements have 10 nodes each, so the more elements you add, the number of nodes can exponentially increase. Personally, I look at the target accuracy and max stress. I like to look at them separately, so I make 2 plots. If you check both at the same time, it normalizes them and can be a bit odd to look at other than to compare the 2. Here's an image of the curves from the second study I ran. I was shooting for 99% accuracy, so it technically didn't converge on my first run. I clicked Run again and ran for another 3 loops before converging. Look at the second set of graphs. I can be fairly confident I'm getting correct values for the stress at the max location. So now we know what H stands for. The next question is, what is a P element? I'll bring back the image from earlier of our 2 element types, draft and high quality, first and second order. P elements are all high quality elements. The P stands for polynomial. So a p-adaptive study basically changes the equation describing the legs of our elements. In this image, we see the equations for P and H elements. The adaptive part of the equation just adds exponential terms to the equation. The default for high quality element is 2 or second order. Right? That's where it starts off. If we jump to the p-adaptive section of our study properties, we see we can adjust the starting and maximum order. 5 is the maximum order that's currently supported. I typically don't change these settings since we're starting at 2 as an initial order anyway, and we might as well go up to 5. Maximum number of loops from 2 to 5, you're always going to get 4, right? 2, 3, 4, and 5. An added benefit to running a p-adaptive study is that you can actually tell it what to converge on or what to focus on. You can choose total strain energy, displacement, or stress. If we take a look at the result plots from a p-adaptive study, we can see the max stress in it is about the same place and about the same value as an h-adaptive study. It's about 554 MPa. Since the mesh is so large, the elements can get up fairly distorted. We'll come back to that later. Just like in previous studies, initial mesh matters here as well. In this image, we can see an overly coarse mesh with very distorted elements, giving us about the same stresses as before. In this image, I refined the mesh, and we see a similar stress profile with a stress roughly the same as before. It's within 10%. So we're still getting over 500 MPa in roughly the same location, but the elements aren't quite as distorted. So what did the p-adaptive study buy me here? In this case, not much. The study solved faster since the mesh was much more coarse than the final h-adaptive study. And that's where p-adaptive has its advantage. In a model or assembly where the mesh has the potential to bring your computer to its knees, p-adaptive will not add any more elements. We can also plot convergence graphs for p-adaptive studies. I typically plot max stress with these. You can see here that it only ran 4 times. Hitting run again will restart the analysis since it's only changing the polynomial order and can't go above 5. So it'll run it with a second order, third order, fourth order, and fifth order right from scratch. So here we may have an issue with convergence. In this case, it's because this message comes up when the study starts running. Jacobian ratio is beyond the limit for an element. I clicked yes, just so it would get some results. But what the heck is a Jacobian? The Jacobian is a measure of the curvature or distortion of a higher order element. A Jacobian value of 1 is the tetrahedral equivalent of an equilateral triangle. All sides equal and no distortion. While this is ideal, it's almost never feasible. Based on some studies done, a Jacobian ratio of less than 40 is acceptable. I like to shoot for less than 20. If the Jacobian is negative, it indicates a highly distorted element. Basically, it turned inside out, and the simulation solver will definitely crash. Let's jump into SOLIDWORKS and I'll show you how to interrogate our mesh to check for Jacobian and aspect ratio, which is just as important. Okay, so here we have our model, and I'm going to create a new mesh on this. And here I'm going to use a standard mesh. As I mentioned earlier, the difference between a high quality mesh and a draft quality mesh is just a checkbox right here. If you check draft quality, it'll give you those first order elements. And if you uncheck it, which by default it's unchecked, it'll give you the high quality second order elements. So what I'm going to do is I'm actually going to create a very, very coarse mesh here, and it'll mesh almost instantly. We can see this is a highly inappropriate mesh for my geometry, but I did this for a reason. Because what I want to do is I want to create some plots before I even solve my model. I want to create some plots to take a look if this mesh is appropriate. We can right click on the mesh and go to Mesh Quality Plot. And in our Mesh Quality Plot, we have 3 options: Mesh, Aspect Ratio, and Jacobian. Since we were just talking about Jacobian, let's start there. All right, here we have a Jacobian plot. The maximum Jacobian is 4.1, so that's actually very small. There's not a ton of really distorted elements in here, which is surprising. I would have expected it to distort them quite a bit over here, but because the fillet is so small, the aspect ratio can't get too high, and I don't think it can distort the elements too far. So actually the Jacobian is not too bad in this particular model. I'll edit the definition of this instead of redoing it, and we'll plot the aspect ratio. The aspect ratio is obviously the ratio of the length to the width of our elements. And we can see here we have a max aspect ratio of about 13 or 14. Still not too bad. Some high aspect ratio elements over here and maybe in this area. Maybe something to be concerned about that I'd want to check later on. I'm going to go ahead and run this study. So I'll just click on Run. And I already have an H-adaptive study set up. If we take a look at the results here, we have a max stress of 5.46 MPa in the area that we would expect. Some ways that we can take a look at whether or not this has come to convergence, because I did not get the message pop-up box that said that we have come to convergence, is I can plot the adaptive convergence graph. And we're going to just plot the maximum von Mises stress. We can see that this ran all 5 times, 1, 2, 3, 4, 5, and it's fairly close to converging. Okay, with a max stress of about 5.5 MPa. This is close to convergence. I could certainly run it again. If we take a look at the mesh here, just by showing the mesh, we can see that it did add some mesh to there, and because of mesh coursing, it coarsened the mesh in this area. If I click run one more time without remeshing, remember, it'll run again. Okay, it is completed running, and let's take a look at that von Mises graph one more time. You can see it's still pretty much about 5.5 MPa. We're pretty close to convergence here. I bet you if I ran it one more time, I'd probably get within that 98% that's specified in the study properties. If we take a look at the mesh one more time, we can see it got significantly finer in this area. So let's take a look at some other plots now. We'll plot the stress again. And if I zoom in, we can see that the stress is concentrated very, very tightly in this corner, which is where we would expect, right? If I take a look at the definition of the stress plot, I can choose to show under advanced options, nodal values or element values. Nodal values basically takes all the nodes in a certain area and averages them out, giving you a nice smooth contour for your colors. Element values only averages the stresses of each element and colors the entire element that value. What that does is it gives us a very good idea if I have any elemental hotspots. In this case, we can see that all the elements in this area are there's a nice smooth transition between the hot elements and they cool off very, very quickly. They cool off very, very smoothly. If I rerun this again, I'm going to turn H adaptive off. Okay, and I will rerun this again with a very, very coarse mesh. And we can see that there is one element that's very hot. Okay, that tells me that I really haven't, that gives me a good idea that it has not come to convergence in this area yet. Okay, and in fact, you can see the stress is very, very low. We were looking at 5.5 before. We're only at about half that. Okay, so that's yet another way you can tell whether or not you're at a mesh independent solution, is with elemental values on your stress plot. Again, that's an edit definition under advanced options, elemental values. Okay, as opposed to nodal values, which if I show that actually looks pretty good. That doesn't really give you a huge red flag there. You know, with the elemental values, it does. Finally, the last graph, or the last plot that I'm going to show, is the energy norm plot. Again, that is a stress plot, and it's down here, energy norm error. We click OK to that one, and we can see that there are some errors. There's a lot of errors in this area. If any of them were bright red, I'd obviously be much more concerned about it. In this case, though, we can see there's a lot of differing colors in this area. I'm going to run this one more time with my H adaptive turned on. And as this is running, we can see that the error is kind of normalizing out. Okay, the max has moved far away from my areas of concern, and my error in this area has gone down to 0.005%. Okay, so significantly lower than it was before. Okay, the max is way up here. I'm not really concerned about this area. I don't really have to worry about it. I'm really only concerned about this corner right here. Okay, really quick, let's recap. In this presentation, we've been mostly discussing high quality solid elements. We know simulation offers other types as well. The difference between draft and high quality is the number of nodes and the equations that describe the legs that connect those nodes. Adaptive studies change the element size in the areas it thinks are high stresses, but it's really checking the energy norm error, which I showed you how to plot in post-process. You can set convergence criteria and allow it to ignore localized stress concentrators with the accuracy bias slider. If it doesn't converge, you can run it again and it'll pick up where it left off, further refining the mesh. We want to use our adaptive convergence plots to hopefully end up with curves that look like this. This will give us confidence in our results. P-adaptive studies don't change the size of our mesh, but rather the order of the polynomial describing the sides of our tetrahedrons. You can control which criteria it converges on, and it'll allow you to run an adaptive study with a more coarse mesh conforming to your model. This is nice if you have large assemblies or a lot of really small features where you don't want to devote the system resources to throwing a lot of mesh at a lot of really small features. Finally, with any mesh, not just adaptive, you're going to want to run some post-processing to verify that your elements are not overly distorted in either curvature or aspect ratio. We can also look at the energy norm plots and elemental value plots to check for jagged lines or individual elements that stand out. Thank you very much for your time today. I'm going to stay on the line for a few minutes. Again, my name is Franco Rotoli. I'm a Senior Applications Engineer here at CADimensions. And I'll stay on the line for a few minutes for questions. Or if you prefer, you can call or email me directly. You can always put in a case on our CADimensions website, CADimensions.com. Thanks again for joining. And like I said, I'll stay on for a few minutes. If you want to put in your questions in the chat, I'll be happy to answer you. Thanks again. Take care.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.